Hello, everyone, and today we are going to talk about the fundamental theorem of orders exercises. We are going to go through some problems that can be solved by FTO. Um, and yeah, let's go straight to it. And exercise one. It is to find all n such that n is divisible by 2 to the power of n minus 1. Yeah, feel free to pause and ponder, and I will talk about this. So we've encountered something like this. We can again write it as the modular arithmetic form, which is better to understand, at least for me. Um, but the thing is, n can be composite number, and we didn't study any property about composite number. We all talk about prime, more about the order modular prime. So we can how we turn this into a prime problem. We can consider we can consider a p for any we can consider any prime divisor of n. For any prime divisor of n, we have 2 to the power of n is also congruent to 1 mod p, right? And how can we do next? We have another very important famous little theorem. Again, there's two equations, and two equations. Of course, we kind of like because of we've encountered many times. We can write it like this: the GCD of the two uh exponential. We still it holds. Um, Here, when we think about this, it's how about if you try for some n, you will find it's hard to find an n, and we guess if there doesn't exist any n except n equals 1, which is the trivial case where 1 divides 1 to the power 2 to the power of 1 minus 1. And this is then, but when n is greater than 1, we don't find any suitable n. So um let's see if because here this equation holds for every prime that is a divisor of n. um if we can take a prime that makes this GCD equal to 1, which is very well, and yeah, indeed, if we consider the smallest prime divisor p, if it is the smallest prime divisor of p of n, uh then the GCD of n p minus 1 should be 1, right? Because p minus 1 uh because n's smallest divisor is p, then p minus 1 cannot be a divisor of n. Therefore, n and p minus 1's greatest common divisor, they are coprime. We can choose every smallest pre for every given natural number n. So we know that here we have 2 is congruent to 1 mod p, and this is impossible when p is larger than 1. And therefore we've finished our proof, which is there does not exist any n such that um, this divisibility holds. Yeah, we finished our proof. Let's see another example about exponential function. Sorry, It's about an exponential. It's about so exercise 2. For every prime divisors of 2 to the power of 2 to the power of n plus 1, uh we have p should mod 1 should congruent to 1 mod 2n plus 1, mod 2 to the power of n plus 1, right? Again, this is very similar to what, yeah, you see here. Here is essentially what we are talking in the previous video. It's about complex, quote unquote, complex number of modular arithmetic, right? And this is kind of we don't know anything. We just know something about famous Christmas theorem, and it gives us that p should be congruent to 1 mod 4, but it doesn't matter because of course p is congruent to 1 mod 4. But yeah, but we can kind of square it, and we got something similar to order, which is this one. But think about this: the only possible divisor of this whole expression is 2. Um, there's some sense that maybe this is the order, because the one less than it isn't the order, and maybe this indeed is the order of p of 2, right? Can you understand what I'm talking about? Because 2 to the power of n is an order, but 2 to the power of n plus 1 is congruent to 1. So we think, we guess maybe this indeed is the order of mod p of 2. So we try to prove this. How can we prove this? Yeah, we can prove this like this. We say if we take 2 to the power of k as the order, then 2 to the power of 2 to the power of k is congruent to 1 mod p, right? But here is the thing. We can always square it, and this is still congruent to 1, right? And when we square it, essentially we are adding 1 up in k. And finally, after many steps, we can get to 2 to the power of 2 to the power of n. But n isn't, if k, but n is congruent to -1 and doesn't congruent to 1. As a result, we know that k plus 1 should be equal to n plus 1. Sorry, k should be equal to n plus 1. And it gives us that 2 to the power of n plus 1 is indeed the order. And this is great, because what we want to show is that p is equal congruent to 1 mod 2 to the power of n plus 1. Well, we get this. We get 2 to the power of n plus 1. And let's think about what can we get now. Because 2 to the power of n plus 1 is the order. We know that 2 to the power of n plus 1 should divide p minus 1, right? And it directly gives us the desired result. And this is very obvious when we think about the famous little theorem. And we finished our proof. And this is the two exercise problems that I went through, and hope you enjoy, and see you next time.